Yesterday we defined simple harmonic motion as motion in which the restoring force is directly proportional to the displacement. In other words, the more you stretch a spring, the more force is required to stretch it, and therefore the more force that it pulls back with, the restoring force that it pulls back with, okay? The bigger the displacement, the bigger the force. Now, we did this. Yesterday wasn't the first day we did this. Yesterday was the first day we called it simple harmonic motion. But way back in our dynamics unit, when we were talking about energy, spring potential energy, elastic potential energy, we really did simple harmonic motion. Remember we said F is equal to K times X? You guys remember what that equation is? It's called something law, somebody's law. Good, Hooke's law. Hooke's law says F is equal to K times X. That is simple harmonic motion. Look, this equation tells us that as X goes up, what happens to F? F goes up. The force is directly proportional to the displacement. Now, how does that manifest itself? If the force gets bigger as the displacement gets bigger, what that usually ends up meaning, what usually ends up happening, is the motion ends up repeating itself. When we let a spring go, it vibrates back and forth, back and forth, back and forth, motion that repeats itself. When we pull a pendulum back further and further and further, and then we let it go, what happens? Well, the pendulum goes back and forth, back and forth, back and forth. So motion in which the restoring force is proportional to the displacement usually manifests itself in motion that repeats itself, like a pendulum going back and forth, or like a spring vibrating back and forth, back and forth. The frequency, we defined almost the same way as we did in our circular motion unit. Circular motion, it was the number of revolutions per unit time. Here we're going to say it's the number of cycles per unit time. The number of cycles per time. So the number of, showed you a few minutes ago, the diagram of the pendulum, the swinging ship at the amusement park. Okay, we want to measure the period for the time that it goes from here, position 1 to position 2, and then back to position 1. Okay, frequency is the number of those cycles, not this, okay, but the number of this per unit time, the number of cycles over the time. The units would be hertz. Period, capital T, not a lowercase t, would be exactly the opposite, the inverse. It would be the time over the number of cycles. When you're at the amusement park on Friday, measuring the period of that swinging ship going back and forth, the period of one cycle is high enough that you're likely going to be able to measure the time fairly accurately for one cycle. But it's probably better if you try to measure the time for 5 cycles. Okay, watch it going back and forth, back and forth, back and forth 5 times. Get that time. Then what do you do to find the period? Take that time and divide it by 5. Divide it by the number of cycles that have just taken place. Does that make sense? What's the equation that appears on our data sheet that relates the two of these together? F and T, frequency and time. Garrett? Good. T is equal to 1 over F, or F is equal to 1 over T. Again, you're going to need to use these equations. They're not on your data sheet. It comes down to the definition. The last equation, F is equal to 1 over T, is on your data sheet, and we can use that. We did some questions on 345. I think they went okay. No problems with those? We talked about a pendulum after that. A pendulum as an example of simple harmonic motion. An example that isn't truly simple harmonic, but is really, really close when you're dealing with small angles, angles of below about 40 degrees. We discovered that there were only 2 things that affected the period of the pendulum. There were a lot of things that we thought would affect the period of the pendulum, Jazzy, but there were only 2 things that really did, Jazzy, affect the period of the pendulum. We thought the mass would. Well, it turned out the mass didn't matter. We thought the initial angle would. Well, as long as the initial angle is below about 40 degrees, the initial angle doesn't matter. The only 2 things that we found that affected the period of the pendulum were the length and gravity. 9.81 versus 1.6 on the movie. This equation, we said, also appears on your data sheet, but we have to be able to solve for the other 2 variables in there, L and G. Let's do that again. T is equal to 2 pi square root L over G. Let's solve for L. Okay, let's take the 2 pi over by dividing. We get T over 2 pi equals square root L over G. Let's take the square root over by squaring. It becomes T over 2 pi squared equals L over G. Let's take the G up by multiplying, and we end up getting G times T over 2 pi squared. Now, this equation you might have to use, but it's not on your data sheet. So be prepared to rearrange it just like we just did. Want to solve for G? Want to solve for G? When we go to the step that we just went to, G is equal to G times T over 2 pi squared, and then let's take the T over 2 pi squared down by dividing. So G becomes equal to L over T over 2 pi squared. That's not a very nice looking equation. L over T over 2 times pi with all the bottoms squared. It's not a nice looking equation, but it's the best we got. So we got to go with it, okay? Be prepared again to rearrange it to solve for either L or G. Now, we did an example on 379, and we did some practice problems on page 379 as well. Any issues with those practice problems on page 379? No? You guys are superstars, and you guys are all prepared already for our field trip on Friday. Here's the new thing for today, and it's a short one. I'll spend a few minutes talking about this, and then we'll see if we have time to go over our tests here. Resonance. Well, let me define another term first. Let me define resonant frequency. If I can spell it. Resonant frequency. Everything has a resonant frequency. Everything has a natural frequency at which it wants to vibrate. My larynx right now, my voice box, is vibrating at a particular frequency. My voice box vibrates at a different frequency than your voice box does. That's how you can distinguish my voice from your friend's voice, because they all vibrate at different frequencies. They all have a natural frequency at which they want to vibrate. Okay, if I hit this desk, the desk has a natural frequency at which it wants to vibrate. That natural frequency is the sound that you just heard. Okay? When you put your finger on a doorbell, it goes ding dong. Okay, what happens is a hammer ends up hitting a piece of steel that's a short piece of steel, makes the ding, and then the hammer falls and hits a longer piece of steel, which makes the dong. Ding dong. Okay, the short piece of steel has a frequency at which it wants to vibrate. The long piece of steel has a frequency at which it wants to vibrate that is a lower pitch, a lower frequency than the short one. Okay. A meter stick has a frequency at which it wants to vibrate. Okay, right now the meter stick is effectively 40 centimeters long because there's 40 centimeters hanging over the edge and I'm holding it tight right at the edge. Okay, I flick it. You can hear that meter stick vibrating back and forth. There's a very particular frequency, a natural frequency, a resonant frequency at which the meter stick wants to vibrate. If I make it 70 centimeters long, it has a different frequency at which it wants to vibrate, a different resonant or natural frequency. A lower pitch, right? Remember the piece of steel in the doorbell that was longer created the dong? The piece of steel that was shorter created the ding, the higher pitch? Okay, when we have a shorter thing, like what was it, a 40 centimeter long meter stick? It was the higher pitch. When we had the 70 centimeters, it was the shorter pitch, right? Even something like a swing set. A swing set. Okay, right now I'm holding up the keys, acting as my swing set here. It has a natural frequency at which it wants to vibrate. We can change it. We can change the natural frequency by changing the length of the swing set, right? But as long as the conditions don't change, it has a very particular natural or resonant frequency at which it wants to vibrate, right, Ryan? That's resonant frequency. Let's define this in words here now on the board, and then we'll talk about how that relates to this phenomenon called the resonance. The resonant frequency, the natural frequency at which an object, any object, every object, wants to vibrate. We'll put wants in quotation marks. Wants to vibrate. Water has a natural frequency at which it wants to vibrate, a resonant frequency. Water's resonant frequency is in the range of 2.4 gigahertz, 2.4 billion hertz. That's why your microwave oven produces microwaves at a frequency of about 2.4 gigahertz. Microwaves work on the principle that water will resonate or vibrate at the frequency that of the microwaves that hit it. If we hit it with microwaves at that frequency, then we cause the water molecules in your food to start vibrating, and that heats up your food. Okay, the vibrating water molecules. If you have completely dry food with no water molecules in it whatsoever, then your microwave isn't going to heat up your food. It only works when there's water in that food. The natural frequency at which an object or water or whatever wants to vibrate. Now, what's resonance? You guys have all seen it before, whether you realize it or not. Resonance occurs when you apply a disturbance at the resonant frequency. So in other words, if the resonant frequency of a swing set is this, okay, it's going back and forth by itself, just under its own volition here, a natural or resonant frequency at this rate. If I apply a disturbance at that natural frequency, now, versus now. If I apply it at the natural frequency of the swing set, what happens? The disturbance grows. The amplitude of the disturbance gets higher and higher and higher. Right, we've seen that on a swing set, right? When you pump on a swing set, you do it at the resonant frequency. When you push somebody else on a swing, you do it at the natural frequency, the resonant frequency. The disturbance grows, sometimes to the point where it's out of control. You guys have probably seen on TV or in a movie or something, an opera singer. Okay, an opera singer sings a really high pitch, loud, the glass breaks. You guys ever seen that? Is that possible, by the way? Sure, it's possible. It would be very, very difficult to do, but it's possible. The glass has a resonant frequency at which it wants to vibrate. When the opera singer matches that resonant frequency, applies the disturbance at that same frequency as the natural frequency of the glass, what happens? The glass starts vibrating more and more and more and more, just like the swing set started vibrating more and more and more. Well, at some point, maybe the glass breaks. So resonance is the phenomenon where a disturbance is applied, or a force is applied, I should say, at the resonant frequency of an object. This causes the object to vibrate and causes the amplitude of the vibration to grow. There's a pretty famous bridge called the Tacoma Narrows Bridge. It was built in Washington State, a place called Tacoma, Washington. I think it was around 60 years ago. I think it was maybe 50s. I can't remember the date exactly. Even when it was under construction, people saw it swaying quite a bit in the wind. Now, bridges are supposed to move in the wind, same as buildings. Really, really tall buildings can move as much as a meter or two in the wind at the top. Now, that sounds kind of scary. If you're at the top of an 80 story tall building, the building is going back and forth as much as a meter in the wind. That's a good thing, because if it's rigid, what's going to happen to it in the strong wind? It's going to break. It's going to break off, right? So you want it to move a little bit, but you don't want it to move like crazy. Okay, people noticed in this Tacoma Narrows Bridge that it was vibrating more than normal, like a vibration that you could actually see, physically see. So they finish it, they open it up. In 6 months after they open it up, less than 6 months I think it was after they open it up, it's windy one day. Not crazy windy, not like, hurricane force winds or anything like that, but it's a bit windy, and it's gusting. And it's gusting at the frequency, the natural frequency of the bridge. So what happens to the bridge? It starts vibrating. The amplitude of the disturbance, the amplitude of the vibration starts growing and growing and growing, more and more and more. What happens eventually to the bridge? Falls apart. Okay, the bridge literally falls apart because of resonance. Just the same as the glass that the opera singer was singing beside broke because of resonance. Just because, for the same reason as when your little brother or sister's on the swing set and you're pushing them back and forth more and more, the disturbance grows and grows and grows. Maybe to the point, if you go crazy with it, to the point where they fall off, because you're pushing them so high. Okay? Resonance is that phenomenon whereby there's a force applied at the natural frequency which causes the disturbance to grow and grow and grow, maybe even to the point where it breaks. So what's the frequency at which this can happen? Well, if we're talking about something like a swing set, right? The disturbance grows and grows and grows as you push it and push it and push it at the resonant frequency of the swing set. Well, we can say the natural frequency is 1 over the period. Well, the natural period of the swing set would be 1 over what? You guys know this. We just did it. 2 pi square root F over G. So you can see that unless we change the length of the swing set, it's going to have a very particular resonant frequency. It isn't going to change. It's going to be the same. That's why you have to push the swing set at the right time. You can't push your little brother or sister at random intervals. You're not going to get the swing set grow, or you're not going to get the swing, the amplitude of the swing growing higher and higher unless you push it at just the right time. Does that make sense? Good? All right, that's it.